So the thing that I wanted to do is describe some acts or direction stuff. And I will describe the part of the part of the sense, and then if you want to either we'll try to figure out how much is it in the paper or maybe but let's start. I mean, the beginning would be very simple. I want to put down on the board what is the input to the fact of that field and what gets in the fact of the field. And then we'll start describing what quantities that we can or cannot compute. So, okay, what do we have there? We have this certain function R, right? These are the parameters of our behavior. And then we have Q, which is a prime integer. And then we have principal ideal. But such that in the generator is very small, and let's call very small. Let's call it polynomial. Yeah, I mean, what I mean is polynomial. But let's call it polynomial. Right? So this is one thing we have. Right. Yeah, I will talk about this thing. And not that the function of the security parameter and what and then we have Z, which is this random element in R2. These are the parameters that yeah, I think that would be easier. And change them on and then see. All right. So these are the parameters that define our system, but of course the attacker doesn't see them. G and V are secret in the house. So what does the attacker see? The attacker sees, so this is R and Q are public, but so the attacker sees R, Q, and it sees the following elements, the public parameters. So we had this y, which was a form of, I'm going to use this set of notation. So it's a over z, where that thing meaning in R cube, a over z, where a is okay, so it's not extremely well defined, but once you take this thing and view it as a representative of an element in R2, then so A was chosen at random, alright, even though that one and that one would be this. This would mean choosing at random as a small element, and this means choosing at random as a unit. Okay, so this is, we have an encoding of 1 at level 1. This is what Sandy called an encoding of 1 at level 1 because of Z in the denominator. And it's in cosine. And now we have xi, which is of the form bi over z over q, where bi is a small element itself. Small size. And because this is a principal ideal and because this is in the ideal, it means that bi is of the form bi prime times g. When you think, again, this is when you think about it as an element in R, and when you do this, you think about it as a representation. So, okay, so the attacker has these, and so this is an encoding of 1, many encodings of 0, and the reason we need all of these encodings of 0 is to break this algebraic thing. You don't want to just be multiplying by y, you'd be multiplying by y and then adding encode stuff. And finally, you have the zero testing parameter, which is of the form h v to the k over g, all of that q. K is how much multilinearity we want to get. H is an element which was, I don't know how to say, a random element. It's a small random element, except not that small. And it's R, I don't particularly care what concept it falls in. What I do care is that H, the size of it, is, let's call it U to the half plus epsilon. It's a little bigger than square root of Q, but much smaller than Q itself. And the condition that I need for the zero testing parameter to work as a zero testing parameter is if you take H and multiply it by K of these guys, the result is still significantly smaller. So what it's basically when you do a zero test parameter, you get something at level K, and something at level K you get by some polynomial of degree K in these A's and B's divided by K, and then you multiply it by here. So the polynomial itself would have like 0, 1 coefficients, or breaking multiplication, all the coefficients are small, but the monomials themselves are a product of each monomial is a product of K of these guys. So you take a product of K of these guys, multiply it by H, you really need to get something much smaller than Q, because this is how you test. If it gets cancelled. If the G gets cancelled, then you get one of these, and a couple of those, and a couple of those, and that's it. So we need H times product of K of the GI and A smaller than, I don't know what. This is sort of what we have in the parameters. A good one. Okay. K is parameter lambda security. Parameter n is well, k square, and q is roughly 2 around that. That's a very aggressive setting of parameters, lattice attack-wise. It means take the smallest thing that LLL still fails to build. You can make the parameters less aggressive. I think some of these pieces, but let's see. Okay. So the attack. Okay. So the attacker sees this, and what does the attacker want to do? Well, several cryptanalytical goals would be to recover Z. I'm going to actually write down on the board the multilinear decision Diffie-Hellman problem, because at least some of the things I'm going to describe would be targeted specifically at that. No, not really specifically. So another thing that the attacker may get, so these are the public parameters, and now come the problem instance. So you get UJs, which is the form EJ over Z RQ, where EJ is the random element. And you get W, which is one of the two things. Well, W is of the form C over Z to the K cubed, and it's either and I have to say J goes from 1 up to K plus. So I'm getting K plus 1 encoding of random stuff at level 1, and 1 encoding of something at level K, and I want to know whether that thing that's encoded there happens to be equal to the product of all of these guys. This, where this thing is, this is the parameter we have there. I guess the 8 here and the 7, 8 here is somehow related to y. And then C is either congruent to the product of the EJ, J from 1 to K plus 1, I, or it's a random element of that. And your goal is to tell them that's the by the multilinear. Okay, let's start saying something that you can do here. So let's see. We said when Sanjay was describing the scheme, he said that you cannot really hide the ideal, but so far it's not completely apparent that the ideal is public here. So how can we figure out what the ideal is? So here is how one way to figure out what the ideal is. I think I'm going to ignore these parts for a while, and maybe I'll ignore these parts for a while. Hopefully, things that I'll say will still be true. So, choose R of the I, compute V as product from 1 to R x j times y to the k minus R. So this is an encoding of an element at level k because I took R encodings of 0 and R, k minus R encoding of 1 times the parameter for 0 test. And now R greater than or equal to 1, and I think let's say that I chose just one of the xi's for now. Well, this is an element in the ideal. The numerator is an element in the ideal because I took one of the zeros. So therefore, this thing, the thing written inside of the Q thing, is short. That's the zero test parameter that reads. Which means that this is actually equal. The z's cancel out, the g's cancel out. Well, one of the g's cancel out. I'm going to get j from 1 to R d I j prime times g to the R minus 1. Minus 1 because one of them cancels out over here. If I take the representative, the short representative here, then this equality actually holds without mod. Is my point. Okay. So therefore, this is in particular this is an element in the ideal G that the principal ideal generated by G to the R minus 1. And this is what the zero testing parameter gives you. It actually gives the attacker a lot of power because you can get equality holding not only mod Q, but even over the ring itself. Okay, what can we do with that? So let's think of R equals 1 for now. So you get a bunch of elements in the generated by H. Well, if you get a bunch of elements in the ideal generated by H, then you can hope that, over this ideal, the GCD is H. So here, ignore that part and only use those, and only use R equals 1, then I only have like a K of these guys to work with, and maybe the GCD will not be H. So first of all, maybe it will be, and then if they're not, then I'm going to take a few more of these and throw them in the mix, and then I'm going to get a whole bunch of more. And I'm still going to work with R equal 1, and I'm still going to be fine. So this is repeat until well, GCD of the is do it and take GCD. And you can repeat a few more, and hopefully, no doubt that if you have enough of them, then that can of elements that spans H and then a basis. So at least, well, we can't get H, but we can get the principal ideal generated by H. So that's a start. Well, Then, okay, now we got that. Let's keep the same. Let's do the same thing with r equals 2. And H. So yeah, we can get well, we can get any power of g up to k minus 1. And we can get bases for all of these things. So that's good. So given a basis for H, generate a basis for H inverse. H inverse in the field of phi. Where does this thing live exactly? I mean, this is a principal ideal of what plane? It's a fractional ideal. But nonetheless, it's a lattice. So it has a basis. Okay. Well, we have a basis for this one and a basis for this one. We ought to be able to multiply them. Given a basis for H inverse and for H times G, get a basis for. So we can't really hide the ideal. You can always, and you notice the only smallness thing that we used is that this thing gave us an equality over the ring rather than and we didn't get a small basis of a G or a small basis of H or anything like that. But as algebraic creatures, we actually know what they are. Okay. Let's do something a little more worrisome. Let's look at these again. Nothing particularly special about G that we used here. I mean, we needed one G to cancel out the G in the zero testing parameter. But other than that, I mean, we found the basis to G times H by putting another G here in the numerator. So instead of G, let's put one of the EJs here in the numerator. Okay. I'm going to erase it. Do the same to get the basis of J. Now, if you're a cryptographer, that should really rub you the wrong way. I just computed the split log for you. I gave you a level 1 encoding of EJ, and you computed the actual, well, that's EJ but that's a basis for the principal ideal. Is that the same as the coset? Why is that the same as the coset? I'm blanking out on something here. So I have, oh yeah, just take. I have a generator for that, or you know, a vector there. Let's say there is each time something. I need to. Okay, yeah, I can find. Yeah, I can find the GCD of them, and reduce it maybe, and then the GCD of all of the basis vectors for that has to give me the same cost of each itself. But I have a basis element for this, not necessarily a generator, but a basis element for those. Since they generate the entire thing, what would happen if I compute the GCD over R? What? For all I know, they're all of the form EJ times something. Right. Yeah, I'm going to choose one of these EJs and then one of these XIs that have a zero, so that I have a zero to cancel against this. I have a zero to cancel against this, and all the others I'm going to choose at random, and then I'm going to get EJ times H times a whole bunch of other things. And when I do that, now I'm going to. Now, I mean, the thing that I have to work with is this, is the basis for H. Cancel the H. Oh, sorry, forget it. Don't cancel H. Forget it. Let's just assume that H was in the coset 1, just to make the argument simpler. But if it wasn't in the constant, okay, so I didn't, okay, so I'm going to get eventually something that looks like this, EJ times H, times many different random things, which I can GCD together to get rid of. So eventually I'm going to get, no. Right, it has to be the same. So it's going to be H times something, but it's the same something. That I don't see that either right now. But it was simple last time that I thought about it. Right. Oh, that if I want to get this one specifically. So then, right, the same way I'm going to get A times H times something. And these products I get, this is not the ideal, this is just a product. And then I look at these two things modulo I and basically divide one by the other, and I'm going to get EJ mod I. So I'm going to get the coset of EJ. And that is sort of a discrete log because I gave you a level 1 encoding with Z in the denominator, and I recovered from it something that looks like a level 0 encoding with no Z in the denominator. The only difference is that that's not small. So let's see what happens if I just try to use it as a level 0 encoding. How do you use a level 0 encoding to break DDH? Well, just multiply. So you can multiply k of these, and then for the k plus first, you multiply one of these guys that you got this way. So you do get something that syntactically would look very much like this, except for that condition. Because of this big EJ that you multiply in, that condition will not be satisfied. So when you multiply it by the zero test parameters, you do get a wraparound mod Q, and you will not be able to test it. So this is the only reason why that thing is not, this attack doesn't actually break this multilinear DDH. You can definitely, given these encodings, you can actually recover the individual cosets where the numerator sit. You just cannot find small representations for these cosets. Right. Right. This you can't do because, I mean, the ability to do that rely on the fact that you can throw in one of the zeros so that you cancel this G. And this one is already at level K. You cannot throw in any more of the zeros, otherwise you get a high power z in the denominator, and you want to be able to multiply the zero testing parameter will not cancel out z. All right. So that's, but it is kind of bad. I mean, yeah, maybe DDH, multilinear DDH is not broken, but there are many other assumptions that we like to make in discrete log-based crypto, like if you get encoding of some matrix in the exponent, you can't tell whether the matrix is full rank or not. That's called the linear assumption. A variant of it is called, a special case of it is called the linear assumption. And here you can definitely do that. If you get an encoding at any level other than the top one, you get an encoding at any level other than the top one of a matrix, you can check whether you can actually compute the rank of this matrix and determine everything mod I. But, yeah. So assumptions like that would be just plain. Assumptions saying doing things like that is hard, like the linear assumption is hard, will just be false with this realization of multilinear. Don't use it. I mean, or don't use this the multilinear maps. There are other candidates. So there is the one over the integer, which would be in crypto, and you can take this and make it a little more complicated, use more than a single element to represent each thing, and use the eigenvalue type of thing, and then it seems to be sorted out as well. So far we have shown that you can compute things like the ideal, you can compute the principal ideal defined by H. You can compute the cosets of things. This is all kind of things that you can compute and actually compute with ease. You don't need to do lattice reduction for anything at all. You can also compute things. You can also take R bigger, like say k minus 1 or something. K, maybe even k. So yeah, you can get R equals k, and then you get g to the R minus 1 times h. And that, I'm assuming that you see an expression like that in the first day, where you have a relatively high power of g here, and you can try to think about taking the R minus 1 root of it and hope that the h thing would sort of drop out and would be left with g. No, you actually get an element that looks like that. There is h and maybe some other stuff comes with it, but there's an element that looks like g to the R minus 1 times something, and you can hope that one root of it. And if h and that other things are sort of random and independent of the g, then you can hope that taking a relatively high power of them will just basically get you some close to some known constant and get you g's out of it. That actually doesn't really work with our parameters just because R is bigger. Maybe I'll repeat it. This one is still not an average impact. This is the non-working version of the average impact. There are averaging attacks that could maybe work, or at least almost work, if you choose things. Okay, let's say a few things about things that you. So these are the things that we can compute. This one is still something that we can compute. This one times something, or the ideals generated by this. Let's say some things about things that we want to compute. Things that if we could compute would break this. So first thing, I just to convince you that this is, at least in some sense of the word, a lattice-based crypto system, I want to show you that if you find a short representation, it breaks the scheme. It's not surprising in any way, but it's not trivial, completely trivial either. So suppose you had a short representation of this. What would you do? Okay. So, say you can find a short element in call it which is of the form V times T. So if V is short, then also D is short, for the same reason that the zero test parameter works. You divide by G, that doesn't increase the size too much because G inverse is a number pretty small still. Right, so multiply V by the zero test parameter to get prime zero test. So it's D times G times H times D to the K over G. Of D times H times D to the K. Then multiply this new and improved zero testing parameter that doesn't actually have over G now in its numerator by W, which, let me remind you, was of the form C over V to the K, where C was perhaps the product of K plus 1 of the EJs. And by a product of K of the UJs, which were EJ over Z. And what I want to show you is that if this was really a product here, then I could identify it. So let's see, what do I get? Then we would get V1, which is product by W, which is just D times H times the EJs. Well, K of the EJs, not all of them. J from 1 up to K EJ, and V. Sorry, no. Saying you can do this, but this is at least one way to the other way is shown called H. I want to say something about averaging attacks. Instead of trying to use the GCDs over there to compute the principal ideal spanned by H and let's say by H, I can try to do averaging attack. I just have all kinds of I want to do an average. And if I recover H explicitly, then that's where you can divide it up. What I want to say about that, H is not so small. One in this respect, if you just try to do what the first part of the residual attack does average attack gets really, really good out to get the right thing, then you need exponential but we have in this paper an improvement of this which says that if you get something that is close to it within 1 plus 1 over 4 to be really close to it in the additive sense, then you can also recover it completely. Parameters right. You need 1 plus epsilon, but epsilon has to be more than polynomial, and you need more than polynomial. Samples given, you're only given that many samples. You don't. It's not like a signature you get as many samples as you want. Here you get k of them. These are of I don't know how many. The last thing that I want to say is how you defend against some of these averaging type attacks, and the thing there is, if you let's look at the randomizer, the things of the form B over Z with B in I. Let's say you choose Z at random, and then you choose B from some Gaussian over the ideal. That's all prime times G over Z. So you choose B prime, and then complete if Z over Z, things like that. But now it's so clear that the distribution of your prime and so you can hope that an averaging attack would leak this geometric shape there and would let you break it. So the way to do it is to sample things in a way that doesn't actually depend on G specifically. So the previous way that I had it on the board is already a little better, because now B is just chosen from a Gaussian on the ideal. That Gaussian could have been chosen if you had any small basis of the ideal, not necessarily G itself. So if you believe that not all bases are equivalent, and given one basis you will necessarily be able to recover G itself, then maybe that helps somewhat. Perhaps even a better way of doing that is to look at the ideal functional ideal generated by this. You choose from. I think this is right. You look at the fractional ideal generated by that guy. You choose things over there. You invert them, and this is sort of the characteristic zero variant, and then you map them into the mod Q by identifying y1 over G with 1 over G mod Q. We don't remember the details right now, and I'm not even sure that this is the right one. I thought for some reason we were sampling it from this and inverting it, but now we don't remember why. That's my recollection. I can do that. Yeah, I'm gonna quit both because I don't see how much to say, and now it's pointless to have me looking for the paper. Everybody else can do it. It's either this or it's opposite. The point was more that the way you do it is you do it so that it doesn't depend on the specific. It has to depend on the form that you want to get, but you want it to depend only on the form that you want to get, and not on the specific choice of distribution. And that you can do it. And then you can make the analysis completely heuristic. The distribution that you get doesn't depend on the specific representative. It depends on the fact that the thing that you have in your hand is small, but not on the specific choice.